Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about the method of finite differences in interpolation. This topic is important for BSc and MSc students of physics, mathematics and statistics. The JRF and NET aspirants will also find this topic useful. The complete note of this topic is provided here for your convenience. I hope you enjoy going through it. Now let us come to the topic. In an earlier lecture, we have seen what is interpolation and what is extrapolation. We have two terms. One is the variable which we denote by x, and this is called argument in interpolation. The function of x which is denoted by fx is called entry in interpolation. For example, the variable x may be age, it may be year, it may be height and so on. The function of x, that is fx, may be height. When we take x as age, fx may be taken as height because there is a certain relationship between age and height. If we take the variable x as year, fx may be taken as population because the population varies with the year. There is a different relationship between year and population. Or we can take, if x is taken as year, we can take fx as a rainfall because there is a definite relationship between year and rainfall. If you take x as height, we can take fx as weight because there is a definite relationship between height and weight. Okay, suppose we have two sets of data. The argument x stands for the year. We have the data available for the population from the year 1950 to 2020. So this is the range of the year from 1950 to 2020, and the population is available at the interval of 10 years. It is available for 1950, 1960, 1970 and so on up to 2020. Suppose somehow the population for the year 1970 is missing from the chart. We have lost this data. So how to find it? This 1970 lies between 1950 and 2020. So the method for finding the population or the entry for x that lies between the two extreme values is known as interpolation. ओके, जो दिया हुआ रेंज हमारा है आर्गुमेंट का, उसके बीच का किसी वैल्यू है x का जो मिसिंग है, इसके इस वैल्यू के लिए fx का मान मिसिंग है, तो इसके लिए पता लगाना यदि है हमें, तो इस प्रोसेस को हम बोलते हैं, पता लगाने की प्रक्रिया जो है उसे हम बोलते हैं इंटरपोलेशन. यदि हम चाहते हैं जानना कि हमारा पॉपुलेशन क्या होगा इन 2030, तो आर्गुमेंट जो है हमारे पास अवेलेबल वो है 1950 से लेके 2020 तक. हम चाहते हैं इस रेंज के बियॉन्ड 2030 में क्या होगा पॉपुलेशन, ये जानना चाहते हैं. तो ये रेंज के बाहर जो निकालने की प्रक्रिया होगी पॉपुलेशन की, रेंज के बाहर x का वैल्यू जहाँ तक मालूम है, जिस तक दिया हुआ है x का वैल्यू, उसके बाद का वैल्यू निकालना है अगर fx का, तो उसे हम बोलते हैं, उस प्रक्रिया को बोलते हैं एक्सट्रापोलेशन. ठीक है, तो दिस इज व्हाट वी मीन बाय इंटरपोलेशन एंड एक्सट्रापोलेशन. आर्गुमेंट के दिए हुए रेंज के बीच के किसी वैल्यू के लिए यदि fx का मान निकालना है तो ये हुआ इंटरपोलेशन. यदि आर्गुमेंट के जो दिया हुआ है उसके बियॉन्ड वैल्यू निकालनी है fx का, उसे हम बोलते हैं एक्सट्रापोलेशन. So this must be clear now. So the method of finite differences is a very convenient tool for interpolating figures when the arguments are at equal interval. यदि आर्गुमेंट हमारे इक्वल इंटरवल पर हैं तो मेथड ऑफ फाइनाइट डिफरेंसेस जो है ये वेरी कन्वीनियंट टूल है डेटा को इंटरपोलेट करने का. ओके, assume that the equidistant value of the independent variable x be a plus h, a plus 2h, a plus 3h and so on up to a plus nh. So these are the different arguments which are equidistant from each other. The difference between the two successive or two consecutive values of argument is h, as can be seen from here. The corresponding values of the entries for these values of the arguments are fa, fa plus h, fa plus 2h, fa plus 3h, and so on up to fa plus nh. These are entries and these are the arguments. Okay, now we define certain operators. The operator delta. This is also known as difference operator. We define it as delta fx is defined as fx plus h minus fx, where x may be a plus h, a plus 2h, and so on. First, assume that x equal to a. Then fx will be equal to fa. So delta fx will be delta fa, and delta fa will be equal to fa plus h minus fa. From where this comes? This comes from this relationship. Okay, so we have delta fa is fa plus h minus fa. Next, take x equal to a plus h. So when x is a plus h, then delta of fx is delta f a plus h. So delta f a plus h is equal to f a plus h plus h. This is for x. Okay, so this is fx plus h minus fx. Clear? So delta f a plus h is f a plus 2h minus f a plus h. And this is what we have written here. Similarly, delta f a plus 2h can be written as f a plus 3h minus f a plus 2h. How can you write this? See here. This is f a plus h. Clear? Here also we have f a plus h. So what is written here is here. Okay? And this, the term within the bracket, is f plus 2h, a plus 2h. It is here a plus h and this is a plus 2h. So if this is a plus 2h, then this will be a plus 2h and this will be a plus 3h. Clear? These are known as the first order difference. We can find out the second order differences, which is written as delta square. So delta square fa can be written as delta of delta fa. For delta fa, we can write fa plus h minus fa. Okay, open the bracket. This gives you delta fa plus h minus delta fa. So delta square fa is, now expand this term, delta fa plus h. Delta fa plus h is, see here, a plus 2h, fa plus 2h minus fa plus h. So this comes here. Okay, and then delta fa. Delta fa is fa plus h minus fa. So this comes here. So we have delta square fa. Now open the bracket here. So this is fa plus 2h minus 2fa plus h plus fa. Okay, this is minus fa plus h. This is also minus fa plus h. So adding these two together gives you minus 2fa plus h. Minus minus gives you plus. So this becomes plus here plus fa. Okay. Similarly, the third order difference and fourth order difference can be calculated. These differences of various orders can be conveniently expressed in the form of a table, which is known as finite forward difference table. On the next page, we have shown table 1, which gives you the arguments, entries, and the first two differences. The higher order differences can be similarly calculated. Okay, see here. So we have here table 1. It has 4 columns. The first column gives you the argument. Second column gives you entry. Third column gives you the first order difference, delta fx. And the fourth column gives you second order difference, the delta square fx. So we begin with x equal to a. So entries are a, arguments are a plus h, a plus 2h, a plus 3h, and a plus 4h. So the corresponding entries are fa, fa plus h, fa plus 2h, fa plus 3h, fa plus 4h. Now find the first order difference. How to find it? Take the difference of fa plus h minus fa. So fa plus h minus fa is delta of fa. Okay. Now take the first difference of these two. This is fa plus 2h minus fa plus h. Fa plus 2h minus fa plus h is simply equal to delta fa plus h. Okay, this is by definition. Delta fa plus h is fa plus 2h minus fa plus h. This comes here from this formula. Delta fx is fx plus h minus fx. Okay, so this gives you here. This comes by this rule. Similarly, the difference of these two is fa plus 3h minus fa plus 2h. So this is written as delta f a plus 2h. And finally, the difference of fa plus 4h and fa plus 3h is equal to delta f a plus 3h. So these are the first order differences. Now calculate the second order difference. So second order difference is the difference of delta f a plus h and delta f a, the difference of these two. So see, we have written here this is equal to delta square fa. Now delta square fa is nothing but delta of delta fa. So this is delta, and for delta fa we have fa plus h minus fa. So this is, open the bracket, this gives you delta fa plus h minus delta fa. So this is what is written here. Clear? Now the second order difference of these two is delta f a plus 2h minus delta f a plus h. We write it as delta square f a plus h. Why? See here. Delta square f a plus h is delta of delta f a plus h. And delta f a plus h is delta of f a plus 2h minus f a plus h. Open the bracket. This is delta f a plus 2h minus delta f a plus h. This is what is written here. Clear? Finally, the second order difference of these two is delta f a plus 3h minus delta f a plus 2h. We have written it as delta square f a plus 2h. Why? See here. Delta square f a plus 2h is equal to delta of delta f a plus 2h. This is equal to delta of delta a plus 3h minus f a plus 2h. Open the bracket. This gives you delta of a plus 3h f a plus 3h minus delta f a plus 2h, which is written here. Okay. So this table is known as the forward difference table. Next, we come to another operator. This is the backward difference operator, shown by the inverted triangle, also read as nabla or del. So the backward difference operator nabla is defined as del fx plus h is fx plus h minus fx. And this we have seen earlier that this is simply equal to delta of fx. So delta fx is equal to del of fx plus h. Clear? So table 2 is also known, table 2 which is shown in the next page is also known as the diagonal backward difference table, as the differences are shown in the diagonal pattern. Unless otherwise stated, the interval of differencing is taken as unity. Okay? Remember, nabla fx plus h is equal to delta of fx. This is how the backward difference table is prepared. We have 4 columns here also. The first column gives you the argument. Second column gives you entry. Third column gives you the first backward difference. And fourth column gives you the second order backward difference. So see, first order backward difference is fa plus h minus fa, and this is written as nabla fa plus h. Okay, see here how it comes. We have delta of fx is nabla of fx plus h. This is fx plus h minus fx. So if you put x equal to a, then delta of fa is equal to nabla of fa plus h. And this is equal to fa plus h minus fa. So this is written here. Clear? Similarly, the first order backward difference of these two terms is fa plus 2h minus fa plus h. And this is written as first order backward difference fa plus 2h. Okay. Next one, backward difference of these two is fa plus 3h minus fa plus 2h, and this is written as nabla fa plus 3h. And finally we have the first order backward difference of these two terms. This is written as fa plus 4h minus fa plus 3h. Okay, and this is del fa plus 4h. So these are the first order backward differences in the third column. In the last column, this is the second order backward difference, del square fx. So second order backward difference is the difference of these two terms, del fa plus 2h minus del fa plus h. Okay, and this we write as del square fa plus 2h. Okay, how it comes? See here. X is, let x be equal to a plus h. So delta fx is del fx plus h. For x we write here a plus h plus h. So this is del f a plus 2h. Okay. So del square f a plus 2h is del of del f a plus 2h. Del f a plus 2h is f a plus 2h minus f a plus h. Open the bracket here, you get it as del f a plus 2h minus del f a plus h, which is written here. Okay, so this thing is here. Similarly, the difference of these two is del f a plus 3h minus del f a plus 2h, and this is equal to del square f a plus 3h. This can also be shown like this. You can easily show that this is equal to this one, as we have shown it for the earlier term. And finally, we have the second order backward difference of these two terms is del f a plus 4h minus del f a plus 3h. And this is written as del square f a plus 4h. This can also be shown as we have shown it here. Okay. So you now know how to find out this first order difference, forward difference, and second order forward difference, first order backward difference, and also second order backward difference. Next we have another operator E. When the arguments are at equal interval h, the operator E is defined as E fx is fx plus h. That means operating E on fx has the result of increasing the argument by h. This means that the operator E is equivalent to increasing the argument by the interval of differencing. So we have E square fx can be written as E of fx, and E of fx is fx plus h. So this is again we are operating E on fx plus h. So the argument will be increased by h. So this will be equal to fx plus 2h. So see here, this is E square, so it is 2h. So in general, if this is r, e to the power r, fx, it will become fx plus rh. This is so simple. So if you take h equal to 1 in equation 8, what you get? You get e to the power r fx is fx plus r. So taking r equal to 1, 2, 3 and so on, what we get? E f0. When x is 0, E1 f0. This is f0 plus 1 is f1. This is from this formula. Clear? E square f0 is f0 plus 2 is f2. E cube f0 is f0 plus 3 is equal to f3 and so on. Similarly, E f1, this is equal to e to the power 1 f1. So this is f1 plus 1 is equal to f2. E square f1 is f1 plus 2. This plus this. Okay. So this is f3. E to the power 3 f1 is f1 plus 3. This is equal to f4 and so on. So all these results follows from this equation. Relation between E and delta. We have delta fx equal to fx plus h minus fx. Now, fx plus h is simply equal to E fx. We have just now seen. So this can be written as E fx minus fx. So fx is common in both these terms. So we have delta fx equal to E minus 1 into fx. Since fx is arbitrary, we can write from this equation delta equal to E minus 1. So this is the simple relationship between delta and operator E. Next we have the fundamental theorem of finite differences. If fx be a polynomial of degree n, that is fx is equal to a naught x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus up to an, then delta to the power n fx is equal to a naught factorial n, and this is a constant. How it comes? We have delta to the power n fx is nothing but the nth differential of fx. If you differentiate this equation n times, what do you get? You get a naught into n into n minus 1 into n minus 2 up to 3 to 1. And this is nothing but this is your factorial n. And this is a naught is a constant, n is a constant. So a naught factorial n is a constant. Okay, so we write here delta to the power n fx is a constant. And delta to the power r fx is 0 if r is greater than n. Because if this is a constant and you differentiate this one once more or more than once, because the differential of a constant is 0, this term will always be 0. Okay, so this shows that the nth order difference of polynomial of nth degree is a constant. Higher order differences are all 0. Note that the operator delta, del, and e are defined only when the arguments are at equal intervals. This will be used in solving the problem of interpolation and extrapolation using Newton's forward difference formula, Newton's backward difference formula. I assume you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें, मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.